This is the second example that I want to run for you in using steel bolted connections. In the first example, we checked the connection to make sure it had sufficient capacity for the load given. In this example, I'm setting it up in such a way that we have everything given except for the capacity, and we want to determine how much load the connection can actually carry. And so you'll see I've got two plates, both of them 5 inches wide, both of them a 1/2 inch thick, being held together by 4 3/4 inch diameter bolts. These are A325. I've got a typo there. These are supposed to be X bolts, 325 X bolts. I've also got on this diagram that the plates are A36 steel, and I'm, as a quick reminder, showing you what the area of a bolt is, pi r squared or pi d squared over 4. Most of the students are pretty comfortable with pi r squared, but every once in a while I throw pi d squared over 4 in it, and it messes them up. Just wanted to remind you that those are the same thing. So we're going to run the process the same way, only this time we're going to determine the capacity rather than check the capacity. So let's start with bolt shear. Determine what the capacity is for the bolt condition in the shear failure. So P over NA has to be less than or equal to FV, meaning the allowable shear stress. Notice in this case we're not, this is the actual shear stress that we're working with here, and we just want to rearrange it and solve for the equivalent load that'll cause that. If we go to table 10, oh no, I was okay. From table 10.1, and look up what the shear stress value is for these bolts. It varies for bolts. For the A325X bolts, the shear stress value is equal to 30 KSI. Again, you'll see that in table 10.1. And so now we're ready to plug our math in. We've got 30 KSI. Remember, we've got 4 bolts, and we've got pi times the diameter squared divided by 4, and run that through our calculator, 53.0 kips. Another way that you could run this problem is simply to go to table 10.1 and not actually have to use the equation. If you do that, then you would want to look for A325X bolts, 3/4 inch diameter, and we need to go back to our diagram, and we need to say is it single shear or double shear, because there's only 2 plates. It can only fill in one location. Therefore, it's a single shear condition. And in table 10.1, you will see that the allowable load, this is a load, is 13.3 kips per bolt. And we've got 4 bolts, so 13.3 kips times 4 bolts equals 53.2 kips. You'll notice we got the same answer. Now there is some round off error in this particular problem, and that is simply a function of the values in the table are approximated to a single decimal point as best as they can be. So, all right, got one capacity done. Now let's check our second capacity. We'll do bearing next. Remember that the equation for bearing, the actual bearing stress, was equal to the point load times the thickness times the diameter of the bolt, and all of that has to be equal or less than the allowable bearing, which was 1.2 times the ultimate stress. Again, if you need to go back and reference what these equations mean, we've got that other video that you can do that in. So one thing that we do need is to go to table 5.1. I think that's page 273, and we grab our ultimate stress for 36 KSI still is 58 KSI. And then we're ready to rearrange and solve for the point load. So we've got just rearrange it like that, and we got 4 bolts. We've got a plate thickness of a 1/2 inch. Both plates are the same, so we don't have to worry about that. Checking it twice. 3/4 inch diameter bolts, and then we've got 1.2 times 58 KSI. Run all of that through our calculator, and we find that in bearing we could actually handle 104.4 kips before this thing would want to fail. Now, just like the previous one, we can also go back and use table 10.1. Or sorry, this is the other table. Table 10.2 has the bearing. And so in this table, we would want to look up where the ultimate stress was 58 KSI. That was kind of ugly. KSI. And we've got a 1/2 inch thickness. In the table, we determined that in bearing it can handle 26.1 kips per bolt. Again, we've got 4 bolts, so 26.1 kips times the 4 bolts, and 104.4 kips. In this case, there was no round off error, and it comes out to be the same number. So you can take either approach. You can use the equation, or you can also run with the table. I'm merely showing you both to show you how both procedures work. All right, now we need to check our tension failure, both on the gross area and the net area. So we've got tension on the gross area first. That is failing through the plate. And recall the equation for this. There's our actual stress side, our allowable stress side. We'll go ahead and just substitute that in straight away. 60% of the yield stress. Recall that the yield stress for 36 KSI still is 36 KSI. Rearrange our equation, solve for the point load, and we've got, just rearrange that so you can see that there. 5 inch width, a 1/2 inch thickness, 60% of 36 KSI. Run that through our calculator, and we've got 54 kips. Now there isn't a table to simplify this part of the equation, or sorry, the process, and so you've actually got to use the equation to get the allowable load for tension on the gross area. All right, let's do tension on the net area. This will be our last calculation in the problem. This is a failure that would go through one of the line of bolts. And note in this case, if it was, let's scroll back up, if it was to actually fell through the bolts, it would actually go through 2 bolts, and we need to consider that in our math. So the equation for the actual stress, we've got the adjusted width, which subtracts out the bolt diameters, and we've got that multiplied by the thickness, so there's our area. And on the other side, the allowable is 50% of the ultimate stress. We'll just go ahead and substitute that right in. Recall from table 5.1 that our ultimate stress is 58 KSI. All right, let's do some rearranging like we've done with the previous parts of the problem. You know what, I just messed up. I don't know if somebody caught this, but I put the wrong value right here. This one should be a capital D, which is the bolt hole diameter. So go ahead and correct that. Apologize about that. And finish up here. This is 0.5 times the ultimate stress. Let's plug some values in. The width is 5 inches. I've got 2 bolts that it would fall through. Now note I have 4 bolts total in the connection, but if it falls through the plane of one of those bolts, it would only pass through 2 of them, so that stays 2. We've got 3/4 inch bolts, and we have to add to that a 1/16 of an inch, which in decimal form is 0.0625 inches. That makes our bolt diameter, or sorry, the bolt hole diameter just a little bit larger than the bolt itself, so it can fit through. And all of that has to be multiplied by the thickness. So there we have the area, and then of course we need to multiply that by 50% of the ultimate stress, which is 58 KSI, and plug that in our calculator. Dun dun dun. It magically gives us 48.9 kips as our final value for capacity on the tension on the net area. Now, what does all this mean? We've run 4 different scenarios through there. Rather than scroll up, you're welcome to scroll up. I'm just going to write the summary here. In summary, you have to compare all 4 of these values together. So we've got bolt shear capacity, we've got bearing capacity, we've got tension on the gross area capacity, and we've got tension on the net area capacity that we have solved. And let's just fill those values in. For bolt shear, we discovered that the connection can handle 53 kips. For bearing, it can handle 104.4 kips. Tension on the gross area can handle 54.0 kips. And tension on the net area, it can handle 48.9 kips. Now, what is the total capacity for this particular connection? If we apply a load, the lowest value will fall first, and that is what governs it. And so we're going to look down this list right here and discover that tension along the net area is the failure mechanism that governs here, and this is the capacity of the connection. For the scenario and the loading situation we've been given, the geometry of the steel, the size of the bolts, the type of bolt being used, etc. Tension along the net area governs, and 48.9 kips is the allowable load that can be used on this connection. So that's a problem that, much like the first problem, calculates the values associated with a steel bolt connection. In this case, we ran it the opposite direction and determined the capacity for each of the failure mechanisms, and the lowest one governed, which tells us our capacity for the total connection.